Hello YouTubers, how you doing tonight? I'm putting together this video to help out a buddy of ours, Ron C. He's working on a vintage radio. You should check out his channel. He does a lot of neat stuff. In particular, he's working on an Atwater Kent 67C, which is a farm radio that was designed originally to run on batteries. And he and Brandon are trying to come up with a power supply to convert it to AC powered. And unfortunately this thing's got some really wacky voltages. Let's see what we have here. We have 45 volts, 180, 135, 67 and a half positive, and two negative voltages, 4.5 and minus 45. So I was thinking about it, and the proper way to do this would be to get a custom wound transformer, but that's going to be way out of the ballpark as far as price. So I thought about it. There's got to be a way to do something with off-the-shelf parts. So I started knocking around the idea, throwing some numbers around, doing some calculating, and I thought of a way of using 24 volt AC center tap transformers. I looked on Jameco. They have a transformer like that. It puts out about 400 milliamps, which should be more than enough current to run the radio once we have the supply put together. And the other beauty of it is, with using transformers, you have magnetic isolation from all the different power supply voltages, so you can play with them with ease without interaction between them because they're magnetically coupled, so they're it works out real nice. So what I came up with, first of all, let's talk about the 180 volts power supply. What I did was, we have one of our transformers, I called it T1. It's 120 volts in, 24 volt AC out with a 12 volt center tap. What happens is, what I designed was connected it up as a auto transformer configuration. And what I'm doing is trying to boost the AC voltage. And what I did was, I have the neutral tied to one part of the primary and a hot tied to the other. And with auto transformer configuration, you can jumper the primary to the secondary, and with a little finesse and proper phasing, which is what these dots represent, the proper phase. So I jumpered the primary to the secondary, and I'm going from here to here, and I'm tapping off the center tap. So what I'm doing is 120 volts is being added to the 12 volt secondary center tap voltage, so we're ending up with 132 volts AC nominal. Okay, now all I'm doing is rectifying it, just like Ron and Brandon did in his circuitry, and use 1N 4007s. Now I have pulse DC coming out of here. This is 132 volts RMS. Now when you rectify it, you have pulse DC coming out, and once you filter it, the capacitor captures the peaks, and you actually get more voltage out DC. So without any special resistor ladders or voltage dividers or anything, we go in with the 132 volts AC, rectify it, filter it, we get 185 volts DC out of it, and we should be able to get up to 400 milliamps of current out of this circuit. Okay, now the only other thing about this circuit is the neutral and the negative rail of the rectifier and the capacitor all get tied to chassis ground. Okay, so from chassis ground to this pin coming out, you'll have 185 volts DC, which should be no issue for that radio, because back in the day voltages varied, mains voltage varied, so it was plus or minus 10-15% probably. So 185 volts is minimal compared to the 180 volts required. We should be good to go. So that's the 180 volt supply. Now let's go to the negative rail. Let me realign this. Okay, and we're doing the same thing, except we're adding another twist to the scenario here. What we're doing is we're going to combine secondary windings to add up voltages to get to a voltage level we need. So here's T2, T3, two more 24 volt center tap transformers, and as you see, I have the dot convention. Now the primaries have to be in phase and the secondaries have to be in phase. If we wire this up properly, the voltages of the two transformers will add up. So let's say starting from here, we go from here to here, we have 12 volts. From here to here, we have 24. From here to here, we have 36. From here to here, we have 24 volts AC. So we need the second transformer to boost the voltage from 24 to 36. So we go from here to here, we have 36 volts. From here to here, we have 12. Now, the first part of the circuit is our negative 4.5 volt rail. So what we're doing is we're tapping off the center tap. From here to here is 12 volts AC. We rectify it. Again, now for simplification, I just drew a square to make the drawing a lot easier to see and view and understand. But basically the box here represents these four diodes, 1N 4007s, configured as a bridge rectifier. And I just drew it this way for simplification. So we put in the 12 volts AC, we rectify it like before. We have DC pulses coming out. This captures it and filters it, captures the peak, and we end up with about 18 volts DC across this. And now, since we need 4.5 volts, I put in this LM7905, which is a negative 5 volt voltage regulator. And if you look at it, the one side is tied to the positive rail, and the negative voltage goes into the input of this, and it outputs minus 5 volts here. So now we have 5 volts DC, and we need 4.5. So I added this 1N 4007 to absorb or cause a 6 volt, or I'm sorry, a 0.6 volt forward voltage drop of the diode to knock it down to minus 4.5 volts. Okay, so what happens is we will now end up with minus 4.5 volts. Now, the big difference between the first part was the positive rail of this output is tied to chassis ground in this case. Now we go to the second part. We have 12, 24, and 36 volts. Now we have 36 volts AC going to the rectifier. We rectify it, filter it, and we get about 51 volts DC across the capacitor. Now we need 45, so what I did was I introduced this Zener, 5-watt Zener diode, okay, that will cause a 6 volt drop in the voltage, and so 51 minus 6 volts is 45 volts. So we end up with minus 45 volts DC here. Again, the positive rail of the rectifier and the capacitor go to chassis ground. So when you measure your voltage from here to here, with respect to ground, it'll be minus 45. So we now have our minus 4.5 and our minus 45, and that's our negative rail using two transformers. And the beauty again is, with magnetic isolation of the transformers, these circuits will not interact with the 180 volts or the next one that I'm going to come up with. Now the next sheet is a little more busy, but it's basically the same thing. Again, we're using 24 volt center tap transformers. This is the bridge rectifier represented by these boxes. So let me slide this up. And we have, what I did was, I'm calling this my transformer voltage ladder. So for ease of drawing, I use the bottom of the ladder, and I call this my transformer common only. So the only places these get connected are to these 3 points. Okay, the bottom of the ladder gets tied to this rectifier, and that rectifier. Let me move this down so we can see it, the important part of the circuit. So now we have all these transformers wired up in series, and we have to observe the phase marker so that all these voltages add up. So we have 24, 48, 72, and then 96 volts AC. I got a little overzealous when I was doing the drawing, and I added an extra one. It's not needed, so you just jumper the T5 to T4. Okay, so we start from here. We got 12 volts, 24 volts, and we go up to here and add another 12 volts. We get 36 volts AC, just like we did in the negative 45 volt rail power supply. We rectify it, we filter it, and we get 51 volts peak DC out of this, across this capacitor. Now in this case, the negative rail gets tied to chassis ground. Don't confuse that with this. This is strictly 3 points, 3 rectifiers tied to this point, and that's it. Nothing else gets tied to it. This is tied to chassis ground, and all the negative sides of these positive power supplies get tied to chassis ground. So now we have 51 volts. I'm using the reverse voltage drop on this zener to knock off 6 volts and absorb 6 volts, and I have a slight load on here, a 4.7K 2-watt resistor across there, just to help keep it regulated. And we will have our positive 45 volts DC coming out of this. Next we move up. Oh, did we get out of frame there a little bit? We go to the next level. So we got 12, 24, 36, and 48. So now we have 48 volts doing the same thing. We got a bridge rectifier, which is those 4 1N4007s, or you can buy a discrete rectifier, which would be a little bit easier, less work. Put it in the capacitor, and we end up with, out any additional stuff, 67.5 volts DC. So nice and simple, nice and clean. We have it. We tied the negative of the capacitor and the rectifier bridge to chassis ground. Okay. Then we move up the ladder, and we're adding, 48 and then 72 and so on till we get 96 volts AC. This whole ladder from here to here adds up to 96 volts AC. We connect the bridge rectifier to the bottom of the ladder and to the top of the ladder, and we rectify it and filter it, and we end up with 135 volts, nice and clean. No additional parts required. 135 volts DC out of that. So now we have our 45 volts positive, 67.5, and 135 volts. So that's completes the whole configuration. You've got all 3 supplies. They're all isolated because all these outputs are on the secondary of a transformer. And I looked these up, like I say, they're at Jameco. They're about $9 a piece, so 9 times 7 is what, $63. And you probably have to buy this regulator. If this voltage needs to be exactly 4.5 volts, you could replace this with a LM337 negative voltage regulator and use a pot and dial it in to exactly what you need, which I think you used a LM317 in your circuit somewhere to do a positive adjustable regulator. There is a negative version of that, which is the LM337. So we have all our voltages now. We've got positive 45, positive 180, positive 135, positive 67, and all these B plus voltages are not going to interact, and these aren't going to interact because we all have everything all isolated with transformer magnetic coupling. So I hope you guys look at this. I hope that this solves your problem, which I think it will. Because I believe the problem with the power supply that you were using now is just starving for current. It doesn't have enough current to feed and power the radio properly. And this will have more than enough power because generally 2 radios run on lower currents because of the high voltages that they run at. But you'll have more than enough current. This is a completely all low impedance output, so it'll drive your radio with plenty of power. So good luck. Let me know what you think, and hopefully this does it for you. Bye bye.